All right, welcome everybody. Thank you for joining us. This is the Apalachicola National Eastern Research Reserve's monthly Sci Cafe. This presentation we generally have on the fourth Thursday of the month from 3 to 4. The series highlights research that's being conducted in and around the Apalachicola Bay area. We try to provide plenty of time for questions. I will be taking you off mute so you can ask a question, or you can raise your hand and then if you don't feel like asking it, you can type your questions in the question box. Today we're joined by Harry Mumma. He is with the Apalachicola Reserve's Davidson Fellow, and he attends the University of Notre Dame. He's a PhD candidate, and he's studying ecosystem metabolism in Eastbay, which is over near East Point, the eastern part of the bay. He's using several different instruments that he'll go into to measure CO2 and O2 and other water quality parameters in different areas within the water column. So he's been collecting this data. He's been this fellowship lasts 2 years, and he's been here almost a year and a half. So we're anxious to hear about his study, and his sampling will continue into 2026. So Harry, if you want to take it away.
Oh, well, thank you so much, Anita. And thank you so much for the kind introduction. Before I begin, I'll just preface this by saying this is just a snapshot of the work that I've done so far. And I hopefully I can provide more of a background on what I'm doing. I think it's a little bit esoteric in nature and isn't necessarily easily discernible from just hearing the word flux and like what does that mean? What does that have to do with the environment? Like what's actually going on here? So that's the majority of what this presentation is. And so without further ado, I'll get into it. And so, there we go. What is a flux? I think that's the first question that I should answer. And I think our understanding of fluxes has been, I don't want to say irrevocably, but very damaged in large part thanks to one, popular cultural phenomena, and that would have to be Back to the Future, and specifically the flux capacitor in Back to the Future. And so before we even begin, I want to highlight and say like I'm doing nothing with time travel. There's like nothing involved in like that kind of sphere of things. In fact, it's relatively simple when you compare it to the idea of like what time travel is and like how fluxes are presented in this movie. It might sound like sci-fi or high tech, but in reality, it's not that. It's got a pretty simple definition, and we can break it down together, and then we'll go into its applications. And so I just wanted to start by saying what a flux actually is, and that is a movement of something, right? So fluxes, they occur across a wide variety of different disciplines in science. So it could be a movement of mass, which is what I work on in Apalachicola Bay, a movement of heat, which is studied in large part in terms of like forecasting and like storms generation and like heat exchange in that regard. Energy or electricity, that's another field. Um, so they're all fluxes that are measured. So it's just that movement of something through an area, a unit area, whatever you want to say, whether it's meters squared or feet squared or centimeters squared per unit time. So whatever length of time you're measuring this over. And so hopefully it helped visualize that. I made this little program that hopefully kind of shows it, right? So we have our unit area, which is in this case the red, rectangle or square, and you have particles that are passing through it. And so every second or every time step of this presentation, there are a certain number of particles that pass through it. And so if you were to take each frame and count the number of particles that are passing through at that second, and then do that a few times and take an average, you can come up with an average particle flux in this little animation. So it's a movement of something through space, basically, is the best way to describe it and that I can describe it. So I think after we've answered this question, the second question that comes up is, okay, so we have this movement of things through space. Why do we care about this movement in Apalachicola Bay? And so I have this handy dandy kind of like image which is showing a carbon cycle, but this could be a hydrological cycle, this could be a nitrogen cycle, this could be really the cycling of any species in our environment. And the actual, means in which it cycles or means in which it moves from different reservoirs, for instance, we'll take carbon in the water column to carbon in the atmosphere, that movement is a flux, right? So to study the movement of different things into, I should say, different elements into different reservoirs, right? To study how, for instance, if we take CO2, to study how CO2 is produced in the estuary or how CO2 is consumed in the estuary, right? Like as a carbon sink or carbon source, or for instance, to study like the input of nutrients from rivers into the estuary as a whole. You can look at that as a flux too. It's like, okay, what is the flux of, for instance, nitrate into the river? So I don't want to be cliche and use flux while explaining it, but it's the movement of something somewhere else, pretty much. And that it's a dynamic measurement, but it lets us kind of understand what is happening in the system, right? We're not taking something that is static. We're saying, okay, we have this species and we want to see how it's moving in the system. And so what I've been focusing on, or what the focus of this presentation will be on, is like, okay, how does marine life or marine biota, whether that be, plants or animals, mainly plants on my end, or microorganisms on my end, how does that impact, or how do they impact the flux, and how are they impacted by the flux of other things into the estuary? This is the broader question I'm trying to answer. Connect these fluxes to the the food chain. Whether or not I'll get there, I don't know. But that was the broader question that when I started this fellowship, I was hoping to be able to get to. And so I just want to go into a few specifics of like, okay, so we've mentioned fluxes and we've mentioned that there's the movement of something over unit area per unit time. But what are you actually measuring? Like, what's that something? Can we get to the bottom of? And so, for instance, you can measure what we call production, or you can think of as photosynthesis. And basically, in all of these measurements, this can be photosynthetic production, which would be, the creation of oxygen and the consumption of CO2 by organic matter, or by photosynthesizers for the creation of organic matter. And then there's, the opposite reaction, which is respiration, which is the burning of organic matter, the consumption of oxygen, the production of CO2, right? Those two big things, they kind of tell you about the ecosystem state, right? If you're measuring either the creation or consumption of CO2 or the creation or consumption of O2 in the water column over time, you can get an understanding of whether or not the state is net autotrophic or net heterotrophic in nature. So if we go down to the last bullet point, we look at this net ecosystem production, that's kind of an understanding of, okay, is your environment producing more organic matter, or is it consuming more organic matter? And estuaries are very interesting in this case because they sit at the intersection between oceans and rivers, which are two very different systems. So it's like, okay, you're going to have a system that is more riverine dominated, that has is burning more organic matter, more net heterotrophic, or you're going to have more of like an autotrophic system, and like what are the driving forces and factors behind that? I also mentioned calcification here because it's something I have been looking at, but it's not going to be touched upon in this presentation. But you can look at the growth rate of calcium carbonate in systems. So this is done often over like coral reefs, for instance, to try to get an impact of, okay, are corals growing? Are they decaying? Like how's that looking? So that's one way you can think about environmental fluxes over living systems. Not in Apalachicola Bay, that was a little bit of an aside, just to get an understanding of what it could be. Below I have a figure of kind of like, this is what I'm looking to do, for lack of a better term, right? Understand like, okay, there's an hour of the day. How is that production being impacted, for instance, by PAR? I'm taking PAR measurements. I'm not going to show any PAR data today. I haven't processed that. That's my bad. But hopefully next time, if I get it next time, I can try to tie those two things together. So you're looking at right, how light availability is affecting your oxygen, production in this case. So this is a pretty cool figure, kind of laying that out. And I also wanted to highlight here, hopefully you guys can read this. If not, I can read it for you, which is showing this net production term, which is a flux term. And in this case, there's something that they're measuring is millimoles, right? And then they're measuring it per hour per meter squared. So those are two things to keep in mind. Their unit of time in this case is per hour, and their unit of area is meter squared. That's kind of just a little introduction to the system. So next question you might have is like, okay, so how are these measurements made? And this might be a lot at the moment, but I'm going to go into it and break it down, I promise you. And so we make these measurements by assessing the vertical concentration gradient for dissolved oxygen, O2, that exists in the boundary layer, while simultaneously resolving the turbulent diffusion that is transporting O2. All right, so that's a handful of things, but I promise you we'll break all of those down into what this actually means. And so we'll start by talking about what is turbulence. I think everyone in this call probably has some sort of understanding of what turbulence is. It's the bumps on a plane, for instance. But okay, let's break that down. What do we mean by that? What are we talking about? And so for any history buffs watching, I thought it'd be cool to bring it back to the origins of turbulence. And turbulence as a phenomena was actually first described, and the name turbulence was given by none other than Leonardo da Vinci, actually. So here are a few of his sketches, talking about the turbulent nature. Right on the left, right, you have a body of water, and then you have some rushing water that is emptying into it, and Da Vinci is observing, kind of like these swirls that are created in the water and how they dissipate and how they form and like how they carry and transport things. And in the left, he's also looking at, the same turbulence that is created, like if you have a flowing river and you have a pole or a post in it, the flow around that, and the wake vortices, as we would call them now. He hadn't coined that term yet. But so it's really actually these sketches by Da Vinci and him ruminating on this that he actually came up with this term. He called it turbulenza. And here's a few of the quotes that he came up with describing it. My apologies if they're not really that legible, but I will read them to you. I hope the white text you're able to read. But for instance, he says, observe the motion on the surface of water, which resembles that of hair, which is two motions, of which one is caused by the weight of the hair, the other by the direction of the curls. Thus the water has eddying, as he calls it, motions, one part of which is due to the principal current, the other random and reverse motion. So that kind of gets to the heart of what turbulence is, right? You have sort of flow in a direction, but it's not uniform. It's random. You have a principal flow, but it's not. Your flow velocity isn't the same if you were to take a cross section of that water and look at it, right? There's something that is chaotic in nature in that flow. And he also says the small eddies are almost numberless, and large things are rotated only by large eddies and not by small ones, and small things are turned by both small and large eddies. So we're not going to really get into this, but if you're interested in it, it's really cool. This kind of gets into like the scales of turbulence that exist, and eventually the dissipation of turbulence as heat at the smallest scales, the Kolmogorov, I'm going to butcher that pronunciation, Kolmogorov scales, but we're not going to get to that. We're not going to touch on that, but it's very interesting that, no mathematics here, just kind of like watching and what he's able to derive in terms of turbulence that kind of like speaks to the heart of what it is, which is chaotic flow in nature. And what drives it, which are these eddies, which we'll touch on. Sorry. There we go. And so I think another good way to touch on it, or to touch on what turbulence is and can kind of get an understanding intuitively of what it is to compare laminar flow, which is like, flat flow. I would think the best way I can envision laminar flow is like, think back to like turning on a water fountain, right? And like watching the spout of water come out, right? That's very flat laminar flow, right? Where turbulent flow, as you just talked about, if you think about the water, once it hits something or a pool at the bottom, right? It's spinning, it's chaotic in nature, and it is driven by what we would call, can everyone hear me? Driven, yes, you can.
Yes.
Sorry. Okay, sorry. I was getting a phone.
We had just a little blip. I think it was just momentary.
My headphones are also connected to my phone, and I'm getting a phone call now, but I'm just not answering that and just making sure you guys can hear me. Okay. But okay, so as we go on, so right, what we call the unit of turbulence, or like what is actually causing these turbulences, is what we call eddies, right? The best way I can think about it is like the base unit of turbulence, right? It's not a system of measurement because it's inherently chaotic, but if it was, the eddy would be the base of that. Okay, so that's mine. That's what we're referring to when we say turbulence. Now we're gonna try. I'm gonna try the very best of my ability to illustrate what a boundary layer is. So like, what do we say, or like, what do I mean when I talk about a boundary layer or making this measurement within a boundary layer? And so I think the best way to begin is like this very helpful figure from NASA. Thank you, NASA. And boundary layers occur across fluid mechanics, whether it be in our estuary or like on a spacecraft headed out of the planet. But basically, what I want to say is boundary layers occur when you have a mean flow. You call it a laminar flow, like we just talked about, where you have all your velocities, like your flow velocities pointed in the same direction, very similar magnitudes, right? And then you have like a space where that mean flow has to be zero, right? And so we call that the no slip, or right at the surface of this object, as is illustrated in this image, the flow has to be zero because you don't have any flow at the surface. You have a flow above the surface, no flow at the surface. There has to be some sort of zone, or what we would call a boundary layer, where you go from that laminar flow to no flow at all. And so these boundary layers are often turbulent and unsteady in nature. And we have like this, like we talked about, this could be on a rocket ship, or this could be, for instance, at the bottom of Eastbay, right? You have a mean flow going across Eastbay, but as you get closer to the bottom, you have this turbulent boundary layer that is kind of like doing the bulk of the transport. That's the best way I can explain it at this moment. If anyone has any questions at any moment, please let me know, right? So these flow velocities, or this flow is not uniform. It is very chaotic in nature, right? It is not in unidirectional, it is going in all directions. And this is what we would call a turbulent boundary layer, which is where we're making the measurements across for the purposes of this project. So again, I wanted to mention that in this case, as before we talked about, this turbulent diffusion is being driven by these eddies, or this base unit of turbulence. Okay, so now this might be a jump. If anyone has any questions, please let me know. But basically, what I'm trying to get at, and what we're trying to get at for this work, is we're trying to understand and model the system as a gradient diffusion, right? Where if we measure the concentration gradient within the boundary layer and above it, right? Or you take as many measurements as possible in that vertical direction, right? In that boundary layer, like we can look at that concentration gradient, and we're going to say that this gradient behaves very similar to molecular diffusion. And so I can go into this a little bit if we don't really know, but molecular diffusion basically refers to, like, on a molecular level, right? If you have a concentration gradient of higher concentration, lower concentration on one side, things are going to shift towards the area of lower concentration. That is molecular diffusion at a base simplest level. So we're saying that in our turbulent boundary layer, if we have areas of higher concentration and lower concentration, things are also going to shift down that concentration gradient, but they're not going to be driven by the process of molecular diffusion. That would be very slow. What they're instead driven by is these eddies, these turbulent eddies, which we have previously introduced, right? So there's going to be flux along this concentration gradient, right? Because we have a movement of, in this case, our oxygen particles in space across surface area, and then over time, that's what a flux would be. But that is going to be scaled by the interaction with the turbulent eddies. In this case, we are scaling them by this turbulent diffusivity or eddy diffusivity term. And so this is flux. And this has good agreement with direct measurements of flux, I should say. And this is what we're doing at the bottom of Eastbay, and we're also doing this off Pilot's Cove, or off the Marshall Dock tower, in order to try to understand, okay, so we have, right, for instance, Eastbay, the mudflats. We have microorganisms that are living in these mudflats. How are they producing or consuming oxygen throughout the day, throughout the year? And we'll get more into this. Or for instance, how is the seagrass in off Marshall Dock consuming or producing oxygen throughout the day, throughout the year? And what are the environmental variables that affect this? So this is what we mean when we call it gradient diffusion flux. This is the heart of what we're measuring. If we go back, I can go back to that previous statement of like how this measurement is made. This is what I'm describing, the gradient diffusion flux, where we are, in this case, modeling an diffusivity, but we're measuring the turbulent phenomena that are happening in the water column. And then we are also measuring the concentration gradient of the parameter of interest, in this case, oxygen, in the water column, in an attempt to understand how the ecosystem is behaving. Okay, any questions, please let me know. But that's the breakdown in terms of the background that I will give. I don't have much to say about beyond that, and then now I will go into kind of talking about the project, how we've outlined it, what we've done so far, and I'll share some initial results, and then we can talk about that if anyone has any questions. Okay, so here is a map of beautiful Apalachicola Bay, and highlighted are our two locations or field sites where we're making these measurements. One in Eastbay, the nursery of the bay, in the mudflats off the dock off Carroll Street, and one in closer to Pilot's Cove in Seagrass Meadows off the dock at the Marshall Dock. So we have two very different aspects or parts of the bay that we're measuring, and so I should mention that these measurements are made every month since last October, and we're trying to basically understand, okay, how is production varying throughout the year, and how are different environmental factors like river and flow, for instance, affecting production in these benthic habitats. So we have an understanding or an idea of like the environments we're working in. Here's a photo of our array off the dock, and it's very characteristic, muddy, shallow water off Eastbay Dock. And then we also have, the same array that's gone out this time off the coast of the Marshall Dock. You can kind of see the darker spots. You might not be able to make it out that well, but that's the seagrass meadows. And so there's the array sitting over the seagrass, measuring how productive the seagrass is doing, or how well the seagrass is doing productivity-wise over the course of the deployment. So here is the setup or the system as we currently have it. So I want to make a few statements in regards to this. Sorry, I'm just having to like, every time I touch anything, like I have to reorder the screen. So I will, okay, go from here. Okay, well, this is weird. There we go. Okay. So first thing I'll talk about here is like we have what is highlighted over here is we have the array. And so what makes up the array is this is what is measuring that concentration gradient in space in the estuary. So we have here is an enlarged view of one of the reserves, XO2, a variety of things in the water column. What we're interested in this work is the oxygen in the water column, and that is affected by the salinity and temperature. So of course, the salinity and temperature sensors are important. But we do the full slew of measurements that the reserve makes as well. So we have gradients for all of those. I've not gone and calculated fluxes for anything else yet, but I probably will, and if it's interesting, I'll be certain to share it, of course. So we have this, and then we also have highlighted by these huge black ovals are the pumps that are sitting in the water column. And these pumps are oscillating on and off every 15 minutes to pump water from these two heights into our XO2s, which are then taking the readings. And so basically that is how we're getting the DZ, or as I call it, the DXDZ or DCDZ, depending on how you want to talk about that gradient. in the water column. That's how we're getting that concentration gradient. So that's basically the concentration side of things. Sorry. And then over here is what we call an ADCP, or acoustic Doppler current profiler. This is basically what is resolving those turbulent eddies, as that we talked about earlier, right? This is what is parameterizing, as we call it in the business, the eddy diffusivity term that we talked about, and kind of measuring the flow rate of the water and how the turbulent fluctuations in the boundary layer are occurring. So that is doing the meat of that measurement. And so combined, these two things are how we are making the measurements in the system. There are other things that's displayed here like I'd like to get into. Like we have power sensors on the array, and that's the photosynthetically active radiation, aka, so it's basically measuring the sunlight that is, making its way, like refracting or reflecting its way into the water, and then capable of being used by photosynthesizing organisms. We have surface oxygen measurements that are made as well, but those we'll have to wait for another time. Yeah, so that's kind of the basics of the instrumentation. And my next two and last two slides in the presentation are the data that I have analyzed so far, and I'm going to share with you guys in terms of the actual flux measurements that are taken. So we'll start first in Eastbay. This is last November Eastbay data. You can see the baseline 0 flux, and it should be noted that positive flux means that oxygen is pushing out of the system, or negative flux means oxygen is being consumed in the system, right? So this gives us some understanding of productivity versus respiration. This is over a day-long cycle last November, I should say. And you can see for the most part, the flux is very small. That's the first thing I think you should notice, or I would notice. Not that you should, but I'll explain that, especially if we compare it to the earlier figure I showed you. But this is in micromoles per meter squared per second, right? Before it had been a measurement over an hour. This has been over a couple of seconds, or sorry, a second, I should say. And this measurement is coming from one spot in the estuary. So that micromoles, it's a small unit of measurement. But again, this is every second, and this is from one spot in the estuary. But it gives us an understanding of, like, okay, what is happening in the system over time, right? We can see at times where it's net zero or near zero, which is occurring overnight. And then we see some sustained peaks of consumption, and we see a peak of production. That could be an outlier, followed by more consumption. From what I've seen in the Eastbay data, it is mainly consumption. There's some hungry microorganisms that are consuming oxygen in the water throughout most of the year, as I've seen. But this is kind of like, I just wanted to give like a baseline level of understanding of like what we're producing, or what I should say I'm producing in regards to flux data. But this is just a one-off month, right? It's not compared to anything else. But we can compare it to what happens, for instance, in a seagrass meadow. And I think the first thing to note is that if you go back and forth, the seagrass fluxes are, and you can see this very evidently in the data, orders of magnitude larger than what is happening in the mudflats. And this is to be expected, given I would say I want to say dynamic, but I'll use that word, more dynamic of the environment we're dealing with. But we are dealing with an order of magnitude larger fluxes. Like, we are seeing production at some cases almost like 1 micromole per meter squared per second. That is, if you add that up, that is a lot of oxygen being produced. But then we also see at night, for instance, we see peaks in consumption, which is interesting as well. So like, if you look at the net ecosystem productivity over time, it's not always productive, and in some cases it might not always be outcompeting. Even though it is an autotrophic system, it might not always be net autotrophic, for lack of a better word. But yeah, that's kind of what I've done so far. I'm happy to answer any and all questions. Um, that's like a brief preview. Yeah.
Okay, let's see if we have any questions. Got to give people a few minutes to, I'll unmute everybody. So just note that everybody's unmuted, but if you would raise your hand, that might make it easier. Okay. We have Michael. You want to ask your question? You should be unmuted.
Hey, Harry. Good
Hey, Michael.
presentation. Thank you for the information. I had a question about the data slides that you had. Are those like typically representative of the other data you've seen during the other deployments, or have you noticed that it's like a wide variety?
Yes, I mean, I think there's definitely, like, for instance, in this what we have on screen currently, that overnight low I think is probably an outlier. I don't know if it's representative entirely of the system, but yes, in general, what I have seen, I think the biggest takeaway is what would be expected, which is that seagrass meadows are way more productive than the mudflats. In fact, you can see it in terms of the orders of magnitude larger fluxes. In terms of like the general pattern, yes, overnight you have very low fluxes to no fluxes, and guys, I see this in the literature and then also across deployments. Where during the day, of course, you have peaks in productivity or respiration in that case. Either case, I should say.
Awesome. Thank you.
You're welcome. Thank you.
And to sort of piggyback on that, so why do you have, I mean, the obvious reasons, you have more sunlight than you do in the upper reaches of the bay. Is that the predominant reason, you think?
I mean, I think it's the biggest reason in terms of the overall, yes, production in day as opposed to night. I think in terms of the differentiation in production seasonally, I'm not so sure. I think there could be a lot of factors at play. I do mean to plot and share this with par data because even if it might be, for instance, sunny in spring, you could have increased river inflow, which more turbidity. So I should plot this with both par and turbidity data and get back to you guys in terms of answering that question better. But in terms of the driver of like day versus night, like what you see here, yes, that's the predominant thing. But I can't say as of yet season to season.
Yeah. And I got a little lost, I must admit.
Sorry.
I'm on the social science side. So when you leave your equipment out there year round, correct? Or are you just deploying and taking it back out?
Yes, I take it back out. I mean, a lot of this is powered, like it's not, we don't have power that goes out or runs out to the dock. So this is like, externally powered, whether it be batteries, like B cell batteries, for instance, or the XO2s, like how Michael goes and swaps them. They run out of power. They're not powered on external power. Or for instance, like a lot of like the ADCP, for instance, like they're all like there's nothing. I guess what I'm trying to say is power is a limiting reagent or limiting factor in this, and so they get swapped as not to kill the batteries. So they go out every month, but they do not stay out for the entire month, is what I'm trying to say.
Great. Okay. Do we have any other questions? Give it a few minutes, let people. Oh, okay, Melanie has a question. Melanie, you want to come off? You should be off mute, but.
Oh. Hey, man, those Leonardo da Vinci drawings are amazing. I'm so excited. But I did have a question, well, two questions. One is, are mud flats and seagrass meadows the only two bottoms that you're looking at? And the other one is, are other people measuring what you're measuring either in the river or other estuaries?
First one, yes, those are the only two bottoms. I initially came in here and wanted to do oyster reefs too, but having a subtitle oyster reef that was easily accessible for us proved difficult, so that was taken out of the proposal. So those are the only two bottoms, and yes, other people are doing this. It's not a very, like, in terms of these like benthic flux measurements, like it's not I would say a large field, but there are a few key actors. A lot of work has actually been done not in Apalachicola but in the Chesapeake.
Mm-hmm.
There have been a lot of measurements that have been taken, and then also down in Florida Bay off the Florida Keys. There have been a series of measurements made. But those are like the two most active, I would say, regions. And it really just comes from like a group of like 3 or 4 people who have gone back there repeatedly and made these measurements.
I was just curious about the difference in latitudes and the kinds of grasses and what you would see, but
yes, and yeah, I definitely want to delve more into that, especially like you talk about species and then also production across the different in latitudes. Yes, thank you, Melanie.
it was fabulous.
Yeah.
Thank you.
Yes, I thought of Melanie when I saw those Leonardo da Vinci drawings. It's for those of you who don't know, Melanie does a lot of journaling, nature journaling, and she teaches nature journaling. So I guess Leonardo was one of the first.
Well, just what he could learn without instruments is extraordinary to me.
Yep.
Oh, true. It is amazing. Okay, I am not seeing any other questions. So Harry, thank you so much. I look forward to hearing more of about this in the future. And for everybody attending, thank you for spending time with us. And we wish you happy holidays. And we will see you in January. We're putting together the 2026 schedule this month. So thanks everybody, and thank you so much, Harry. Have a great holiday.